This video introduces applied analog electronics. It corresponds roughly to Chapter 1 of the Applied Analog Electronics textbook. Now, the Applied Analog Electronics course was originally developed for bioengineers at UCSC. It was designed to be, for most of the bioengineers, a first and last course in electronics. As a first course, there's no prerequisite assumptions about having previously had any electronics. Not even the physics, electricity, and magnetism course. We initially required that, but found that it didn't really make much difference. There is an assumption that students have had a little differential calculus. Now, the course is also designed as a last course in electronics in that there is no assumption that students will go on after this course to do more applied design courses in electronics. Some of them will, but that wasn't an assumption. So we wanted to get the students to the point where they actually could do something useful with the electronics that they got in this first course. And that meant that this course became a design course rather than the sort of applied math course that people usually start when they teach electronics. And because it's a design course, and there's quite a bit of theory for electronics, we're doing just-in-time theory. That is to say, we'll only put in theory when you need it in order to do design. And rather than trying to cover all of the theory of electronics, and there's quite a bit of it, we're concentrating mainly on three concepts. The first concept is voltage dividers. This is a simplification of many of the things that are usually used in doing mesh analysis and other more complicated things often taught in electrical engineering courses. But voltage dividers gets you 90% of the way there with 20% of the effort. The second main concept is complex impedance. And we'll use this in a whole bunch of different ways, often in combination with the concept of voltage dividers. And the third major concept is negative feedback amplifiers. And again, we'll use this in conjunction with voltage dividers and complex impedance. Putting these three concepts together will let us get almost all of what we need to do the electronics design in this course. Now, one question that comes up often from students in the class is, why are we teaching electrical engineering? I'm not going to be doing electrical engineering professionally. Why cover it? And there's two main answers. One, very simple one, is sensors. Almost all forms of engineering involve putting sensors into your system in order to measure what's going on. And these sensors are not always, but quite frequently, electronic sensors. And interfacing those electronic sensors to computers is one of the main tasks that you have to do in almost any form of engineering. And understanding how that works, understanding the fairly simple, actually, analog electronics needed to attach a sensor to a computer is what this course is about in terms of the content. There's another reason, though, that's independent of the concept. And there's a lot of learning that happens in this course that, even if you forget all the electronics you learn, is still valuable to have taken the course. And one of the things is that we want to teach engineering design, sort of iterative design where you design something, test it, find out what works and what doesn't, redesign it, test it again, and go through iteration in doing that design. And we want you to be doing that in the real world. Now, for people who are used to doing computer science, they go, oh, we do that iteration and test all the time. The trouble is that software is not running into the problems that real-world design has. I'll get into that in a little bit more in a moment. And on the other hand, the people who do bioengineering, for instance, are used to saying, well, why don't we do this all with wet lab works? And the answer is, wet lab work is very slow. It may take months to grow out a stem cell culture. You can't do a lot of iterative design in a 10-week or 13-week or even 20-week course if you're going to be doing it with wet lab stuff. You get through one iteration and you're done. So if it doesn't work first time, tough. Now, if you're working on a PhD thesis for 5 or 6 years, you've got time to do some iterative design with wet lab work. But we wanted people to get the experience of doing iterative design of really doing debugging on something that had real world complications. So it wasn't just, oh, well, the model says it should behave like this, and if it doesn't behave like that, I've done something wrong. That's the problem with doing it all with computers. If you do it all in simulation and computers, your models are perfect. And that's just not the way engineering works in the real world. No models are perfect. In fact, a big chunk of what engineering is about is picking the appropriate model for the design problem you're addressing. And models come in all levels of complexity, from really, really simple things up to having to deal with quantum mechanical solutions. And if you pick the most detailed model, you'll never get your design done because it just takes forever to do the computation. And if you pick too simple a model, then it doesn't capture the phenomena that you need to model, and things don't work. So, a simple example. We can have a piece of wire. Now, a piece of wire can be modeled in many different ways. The simplest wire is to say, well, this is a metal, it's conducting, and every part of this piece of wire is at the same voltage. It's just what's called a node in electrical design. It's just one thing, and it's all the same voltage. There's no difference from one end of the wire to the other. And for a lot of purposes, that's an excellent model of a wire. It's the simplest one we can use. It's basically saying it's just a single point. And a lot of times that's good enough, but not always. Sometimes if we put a large current through that wire, then we start worrying about, well, wait a minute, there's resistance to this wire. The metal is not a perfect conductor. It's not a superconductor. There's a resistance, and so we'll have a voltage drop from one end to the other due to the current flowing through it. So sometimes we have to model a wire as a resistor. In fact, I have failed some designs as a result of not taking that into consideration. I was powering a motor with the circuit on a breadboard, and I had some wires that I was using to hook up to the motor, and noticed a strange smell and then plastic burning, and it turns out that the wires I was using had too high a resistance for the amount of current I was putting through them. They got hot and started melting the insulation on the wires. I had modeled the wires as, it's just a node, it's all the same voltage, but the resistance mattered in that case. Other times, if you're dealing with a high frequency, you may have to model the wire as an inductor, which we'll get to much later in the course, but it's a more complicated device than a resistor, and at low frequencies, we don't have to worry about it, but at high frequencies, that might be the most important property of that wire. Sometimes, if you've got a couple of wires, you may have to model them as a capacitor, that this wire and this wire, because they're two conductors separated by an insulator, that turns out to be the definition of a capacitor. Most of the time, we don't have to worry about the capacitance, but some of the time, we really will have to care about it. In still other instances, you may have to model it as a transmission line. Now, transmission lines are beyond the scope of this class, so we won't get to anything which needs that sophisticated a model. But as you can see, for just a simple thing like a wire, we may have 5 or 6 different models that we have to choose between. And if we pick the wrong model, we'll either make our design problem much harder than it needs to be, or we'll fail to make our design work because we neglected a property that mattered. And so a big chunk of any sort of engineering design is figuring out what sort of model is appropriate for the system that you're trying to build. Okay, another part of this is that we're very much interested in doing empirical work. That is to say, testing things in the real world. I'm not interested in having people do paper designs. I don't want you to just say, oh, here's a circuit, I designed it, and it'll work, no problem. I want you to build it, and I want you to test it after you've built it. And I want you to debug it, because the chances are that after you build it, it is not going to work. And the question is, why didn't it work? And that's a big thing in all forms of engineering. If you're starting to trying to create new things, some of the things you're going to try to create are not going to work. And you need to figure out why they don't work and how you can change them so that they do work. And that process of debugging, it'll take us all of both halves of this course to get to the point where you can confidently debug even simple circuits. One part of doing any sort of design in engineering are what are called sanity checks. These are basically sort of internal consistency checks you do on your design to make sure that you haven't made any stupid errors. And everybody makes stupid errors. It's not something that as human beings we can avoid doing, but putting in sanity checks means that you can catch those errors before they cause problems. And sanity checks could be simple things like, okay, I'm designing an amplifier, and this amplifier is going to have a gain of 1,000, and I'm going to put in a 200 millivolt signal. Well, 200 millivolt signal multiplied by the gain of 1,000, and I get a 200 volt signal coming out. Now, wait a second, my power supply isn't 200 volts. I'm not going to get 200 volts coming out. Something's wrong. That's sort of sanity check going, okay, was I wrong about the gain of the amplifier? Was I wrong about my power supply? Was I wrong about the size of my input signal? One of those things is wrong because they're not consistent. So doing consistency checks like that are an inherent part of any sort of engineering design. And I'm going to try to get people to the point where they're making these sorts of checks automatically. And it's not a matter of my giving you a checklist and saying, do this, 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 and they'll tell you whether or not your design's working. You need to come up with these sanity checks yourself. You need to be looking at a design that you've come up with and said, okay, what do I have to know to make sure that this is consistent? What things do I check? And that building in sanity checking for everything you design, everything you do, helps enormously in later stages of debugging, because you've then got to the point where you say, I know what the thing's supposed to do. I know what each part of this thing's supposed to do. And so you can, when you build the thing and test it, you can go, I expect to see this size signal here. I expect to see this signal here. I expect to see this signal here. And when you get something that isn't what you expect, that difference between the observation and expectation is what allows you to debug it. You can go, okay, it worked up to here. This signal was still what I wanted, but at this stage, the next stage down, it isn't what I expected. It's probably in this region right here, where it goes from working to not working, that my problem is. And that's decomposition of the problem is a big chunk of what debugging is about. It's narrowing down from the thing doesn't work, help, to this part works, this part works, this part doesn't. Let's look in more detail at this point. Oh, there's a loose wire. Oh, I computed this resistor wrong. That's supposed to be 22 kiloohms, not 220 kiloohms. That sort of narrowing down things and then double checking your expectations versus your observations is really a large part of what debugging is about. Now, people often learn debugging in computer science, in doing programming, and that's an excellent realm in which to learn debugging because your expectations there should be perfect. Things work. When you understand what you're doing, the computer executes it perfectly. And the real world, when we're doing engineering other than computer science, isn't like that. Things don't work perfectly. And quite often the difference between our expectations and our observations indicate some insufficiency in our modeling. Our expectations aren't right because we used too simple a model, or there was some phenomenon that we hadn't thought to take into consideration. And so debugging in the real world is a little bit different from debugging in computer science. And that's one of the reasons for choosing electronics rather than computer science and computer programming as the engineering discipline to teach debugging in. It's just more generally transferable to other engineering disciplines if you do debugging in the real world rather than just in programs. Okay, another thing is this course is not about teaching facts. There's a study sheet in the book that has all the facts you're supposed to memorize. It's one page. That's it. This isn't like a biology course where you may have thousands of facts and words to memorize. There's very little memory work in this. We'll have those three basic concepts, the voltage divider, the complex impedance, the negative feedback amplifier, and we'll use them again and again and again. Slight variations. And the idea is to get you to a point where you can say, oh, I know how to do this. I have the skill of doing these manipulations. And not worrying so much about, oh, I have to memorize this formula, I have to memorize this formula, I have to memorize this formula. Memory work isn't what this course is about. It's about application, being able to design stuff. Let's take a look actually at the specific learning objectives of the course. And these are now specific skills, this is directly from the textbook, of some of the things you should be able to do after you've taken this course. Drawing useful block diagrams for amplifier designs, using simple hand tools, being able to hand solder through-hole parts and some of the larger surface mount parts. These are just basic skills that I expect everybody to develop in the process of doing this course. Using USB-controlled oscilloscopes, function generators, power supplies. Do a whole bunch of stuff with those instruments. Being able to use Python, GNU-plot, and Teradata data acquisition form, waveforms on your own computer. So this is a matter of installing tools and being able to use them. Now, I'm not asking in this course that you be able to program in Python, but I am asking that you be able to take a Python program that's given to you, maybe make some tiny modifications to it, like changing some numbers in it, and run that program. So tools that you need to be able to run, but not necessarily programming. That's in deciding the scope of this course, I decided to stick to analog electronics and leave the programming to other courses. I expect you to be able to do computations that involve impedance using complex numbers. So being able to manipulate complex numbers both algebraically and numerically. You should be able to design single-stage high-pass, band-pass, and low-pass RC filters. RC stands for resistors and capacitors. You should be able to measure impedance as a function of frequency. That's one of the things that the USB-controlled oscilloscope and function generator is really good for. And you'll find that as a simple task once you get to it. You should be able to design, build, and debug simple op-amp-based amplifiers. You should be able to draw schematics using computer-aided design tools. You should be able to write design reports using LaTeX and BibLaTeX. You should be able to plot data and theoretical models on the same plot. Using, here I say GNU-plot, the actual tool there is less important. You could use Matplotlib or MATLAB or other tools. I use GNU-plot because it makes the next step, fitting models to the data, particularly easy. I want to come back a little bit to that third from the last point there, writing design reports. Writing reports is what engineers do for a living. Most of what engineers get paid for is producing documentation for their designs. And most engineers get almost no training at writing. And that's a serious flaw in a lot of education curricula for engineers. And that's one that this course is designed to address. You will spend a lot of time writing design reports for every design you do. And these design reports are going to be the major part of the evaluation of whether you've learned to do things. And I have very high standards for what I expect engineers to be able to write. And this entire chapter of the book that we'll get to, where we talk about nothing but writing those reports, because this is really the product for engineers. I mean, people think of, oh, you designed this hardware. And the answer is, well, yes, but what people take away from that is this report on how the hardware works, and not just, here's a piece of hardware, here's one copy. Okay, other things about the course. Generally, when we do the lab work and the design reports, we'll be working in pairs. And there's two reasons for that. One is, as I mentioned earlier, everybody makes mistakes. It's a lot easier to see somebody else's mistakes than to see your own. And so by working in pairs, if you seriously work in pairs correctly, which is not to say don't just have one person do all the work, but each person does work and compares the results with the other person. When there are discrepancies, tries to figure out who got it right, who got it wrong, where was the mistake made. You both learn a lot more from doing that, and you end up with a better design, a better product than one person working alone. A pair working together properly is stronger than the stronger of the two partners. And so we'll be doing just about everything in partner work, particularly the writing. And the writing doesn't mean you write section 1, I'll write section 2, and we'll just paste it together at the end and be done. That doesn't work very well. Each person is responsible for everything in the report. So you write section 1, he writes section 2, swap. Read each other's work. Any discrepancies, fix them, because there will be discrepancies there. You will have misunderstood something that the other person did, and until that gets resolved, the report is trash. And you need to spend as much time reading your partner's work as you do writing your own work. And that means no last minute stuff. Don't say, oh, the deadline is midnight at Thursday, 10 p.m. on Thursday, I'll start writing. It's not going to work. You need to have time to do the editing, to clean things up, to read each other's work. Don't be a flake on your partner. To avoid that problem of people flaking, generally we'll change partners on every lab. Or sometimes when they're small labs, 2 labs go together for a report. So every report you'll have a new partner. And that means you won't be stuck with a flake for very long. And if you're a freeloader, people are going to soon find out and stop wanting to work with you. And that can be really disastrous later on if you try doing a senior design project or something else. So this is a course where you want to do your share of the work and do it honestly. Okay, that's probably enough on what the course is about as a whole. In subsequent videos, we'll start getting into the actual content of the course.